All right. Thanks so much for organizing this workshop, and thanks for giving me the opportunity to present this work.
You might have to use the mic.
So Andre.
Yeah. Yeah. So if I'm here, okay, I guess it works. Yeah. Okay. Cool. So okay. So I guess our work was well, at least at the beginning, was really inspired by the work of Yuan Wan and Peter Armitage. So I guess it falls along the line of what kind of information can we extract from nonlinear response functions. So of course there are some in few level systems. This is a question that has been studied for a long time, and some of this and so one line of research is how these same signals can be extended to the many body settings. But what we are wondering mainly about is whether there is some unique effect that is unique to extended systems, and in particular due to locality and quasi-particle propagation. And what we found out is that when you have these ingredients, what can happen is that there are long time divergences in perturbative nonlinear response functions. So this is what I will talk about today. So the simplest setting where this shows up is essentially in pumpprobe signals. So here so we imagine preparing this. So at a very cartoonish level, we prepare the system in the ground state. We perturb it by applying a pump. So by coupling the system to a pulse that coupled to some operator A, which we take just to be some extensive operator, and coupling it with strength kappa. Okay, and we let the system evolve for some time tau, and then we measure a 2-point function, AT plus tau, A tau. So okay, so this correlator I will call C kappa, and the pump probe response is just the 2-point function with the subtraction of the 2-point function on top of just the ground state, so without any perturbation. Okay, the statement that we have power law divergences in perturbation theory is this box here. So at lowest order in kappa, so in the perturbation strength, we have a kappa squared times the just unperturbed 2-point correlator on top of the ground state times some power law t to the something, where something is positive, plus higher order in perturbation theory. So okay, so what I will tell you about in this talk is essentially in which system this takes place, and what kind of information can we infer from seeing this kind of power law, if we were to see this kind of power law in an experiment, and also what is the physical meaning of this seemingly divergent signal at long times. Okay. So the two setups that I will talk about are on one hand 1D systems where there is no fractionalization, so our operator can excite just a single quasi-particle, and when scattering processes can take place, then we have just a linear divergence in time. And the second setup, which is essentially is 2D systems where that are topologically ordered, so the quasi-particles are anyons, and just by processes where we can have some braiding, what happens is that the divergence now will be even stronger. So the signal is enhanced by a t to the 3 half. And so the second direction we are particularly excited about because this t to the 3 half, as I will try to explain, is a unique fingerprint of anyons. So one cannot have this t to the 3 half with just local interactions. Okay, so I will jump right in the first part about 1D systems. So here, so in both cases, we think that the story is quite general, and we have a bunch of calculations. So I will really focus on the simplest systems and just the basic picture, the basic physical picture that gives rise to the divergence. And so you can imagine that, so basically for all purposes, you can imagine that I'm talking about just the transfer field Ising model in the paramagnetic phase. So here the ground set is at the cartoon level, just a bunch of spin-up states so polarized along the direction set by the transverse field. And the elementary excitations on top of this ground state are just spin flips. Okay, it turns out that a convenient base to describe the low energy dynamics that has a nice time evolution and at the same time is kind of local are wave packets. So if I have a single wave packet and I create a single wave packet at some point, this wave packet just drifts ballistically with a velocity that is set by the group velocity. And if I have more wave packet, the story remains kind of simple. As long as they're far apart, they just propagate ballistically. And when their trajectory cross, the phase of the wave function picks up a factor S, so the scattering matrix. And in this model, the scattering matrix is just a -1. Okay, so let me mention this picture was inspired by a paper by Sachin and Yang in the 1997. Okay, so so this is the basis that I will use to describe the dynamics. The next thing that I need to tell you about is what is the action of the perturbation in this basis. So the simplest operator that essentially displays the phenomenology that I want to talk to you about is just the order parameter. So notice that we are just imagining here an optical perturbation that couples uniformly throughout the system. So the reason why I'm choosing the order parameter is that the order parameter can excite a single quasi-particle. So the simplest process is that it excites a single wave packet at this we start at some position x0, and crucially, x0 is arbitrary because of this sum over J there. But it can also do more complicated things, like it can excite 3 wave packets. These 3 wave packets will come out roughly at the same point, x0, and then will spread ballistically from there. And again, x0 is something that I would have to integrate over at the end of the calculation. Okay, so this is the picture that I will use to describe dynamics. And the actual quantity that I will care about is this essentially 4-point correlator that is the contribution to the lowest order contribution to the pump probe signal that gives rise to this divergence. So let me point out 2 things. I only care about the connected component of the 4-point correlator. That kind of makes sense by causality. And the other thing that I wanted to point out is that we have an A0, then we go to a T plus tau, and then we go back to A0. So the time order is kind of weird. Well, or if you're very used to nonlinear response, it's your bread and butter, but okay. At the beginning, it was kind of weird for me. So when I will draw the trajectories of the wave packets, note that time goes upward to T plus tau, and then it goes backward again to 0. Okay, so I will just draw the process that will give rise to the divergence. And this, so here, A tau and AT plus tau just exchange a single wave packet. And A0 here creates 3 wave packets that spread out ballistically. The same thing happens for A0 on the other side. And then they meet kind of at T plus tau. Okay, so this is the type of process, but this process is actually disconnected in the way I've drawn it, because this contributes to the product of A0 times the correlator A tau, AT plus tau. So this is not connected. This does not contribute to the pump probe response. But this is just because of the way I've drawn it. If we just shift the trajectories, then it becomes connected because we can have some intersection, and this comes with a phase that is S. Okay, so the claim is that now when I will do the integral over x1, this will give rise to the linear divergence. And the reason for this is that essentially the dependence on x1 is piecewise constant. So as long as there is one scattering event, there is no x1 dependence. And so as long as x1 is in this green segment, the contribution is always the same. So the integral of x1 is just proportional to the length of this red segment, L. And as you can imagine, since everything is happening ballistically, this length is proportional to time t. Okay, so this is the physical origin of this proportional to linear in time divergences due to scattering. But one might ask, okay, but what's the actual physical meaning of this outside of perturbation theory? And the point is that the perturbation theory applies only when the time is smaller compared to the perturbation strength to the -2. So I remind you that kappa is the perturbation strength. And so we can expect that our signal actually is growing linearly up to some time of order kappa to the -2. And but eventually, when you go outside of perturbation theory, we can show that it actually saturates to something that is of order 1. So the meaning of this long time divergence is essentially that at long times you saturate to a signal that is independent of kappa. So it's independent of the strength of the pump. So this is kind of unusual, and it shows up in this divergence in perturbation theory. Okay. Yeah.
So you're working in the gap phase. So
yes.
There the dispersion is the coefficient of t is the fastest speed in the band.
The coefficient of t is a mass that depends on everything.
I see. I shouldn't think of it as a quasi-relativistic kind of a.
Yeah, no.
Because, you know, most places in the Fourier space have no, you know, they're shallow, so there's no speed.
Right.
So what's the meaning of the coefficient of t? I'm sorry.
So yeah, okay. So the meaning of the coefficient is you have to okay. So you have this L thing. This L depends on the velocity of all these quasi-particles. So you have to sum over all the momenta of these intermediate quasi-particles times the amplitude of creating this group of quasi-particles with that thing. So it will depend on the matrix elements times L given that kind of velocity.
I'm just concerned that because most of those quasi-particles are not ballistic. I mean, they're not, you know, there's curvature in the band in most, like.
Yes. Yeah, there's not a.
But there's something survives. Okay.
Yeah, it's definitely non-zero. Yeah.
All right, thanks.
What happens in 2 dimension?
Right. You mean if I just have scattering?
Right.
We have no idea. This kind of process will not survive in 2 dimension, basically, because when you are in 2 dimension, what will happen is that your ingoing particle will be scattered in some other direction, and then it will not be able to recombine there. So at least this kind of complicated process where you create more than one quasi-particle are probably do not exist in our dimension. But you could have maybe simpler processes, but that would require a finite momentum probe, where each of your operator creates just a single quasi-particle, and those should exist also in our dimension.
We expect that the power law will be, say, larger than 1 or smaller than 1.
So okay, as long as you have scattering, the largest power law that you can get is always 1, basically because you need your quasi-particles to be at the same point, and so you can never get something that is larger than 1, even in our dimension. So this actually brings me to the second part of the talk, which is when you have non-local interactions. So non-local statistical interactions. So when you have anyons, you can get a larger power. You can get t to the 3 half.
Sorry, dumb question first. Can you just remind us, just physically, how are we defining this quantity, chi pp?
Yeah, sorry. So it's the linear response on top of the unperturbed state. Yeah, it's so I do the pump probe experiment, and then I just do the 2-point function measurement on top of the ground state, and I subtract the 2.
It's not related to some quant. I mean, it's just really the position of the particle as a function of time.
It's related to the position of.
Well, it's magnetization.
Yeah.
Yeah. So
A
it's
is like a magnetization.
right. So in an Ising model, it's the position because that's proportional to magnetization. If I make this pulse, I guess. But anyway, it's fine to call it magnetization.
Yeah.
But physically, it's just coming because I'm flipping spins, and now if they were down, they become up. And the magnetization is just changing, right?
Okay, so the magnetization is actually so the number of spin flips is actually a finite number, right? So because I'm always
The paramagnetic phase.
yeah, I'm in the paramagnetic phase.
Paramagnetic phase.
Yeah.
Okay. Oh, I see.
This
Okay.
complements what you did, because what you did fractionalizes, right? But here you can create a single spin flip and it propagates a quasi-particle.
I understand.
Yeah, but you could get a similar effect for a 3-point function in the ferromagnetic phase.
The paramagnetic phase.
Yeah. So I guess along the lines. Okay, so right. Okay, so in 3D with anions we can get a t to the 3 alpha. So again, we think that this picture is kind of generic, but we'll talk about the simplest possible setting, which is just a Z2 spin liquid or a perturbed tori code. So there are 2 anion species here, the magnetic anion and the electric anion. And essentially the important part of the story is that when I braid a magnetic anion around an electric one, or the other way around, I pick up an extra phase that is -1. And this is really a non-local effect in a sense. I don't need E and M to come close to each other. So, okay. So this is the first difference. I have these non-local interactions. The second difference is that local operators can only create pairs now, because they can only create objects that are trivial under braiding. So the simplest thing that my operators can do is create pairs of magnetic anions or pair of electric anions. The processes that I talked about before actually kind of go through with very little changes. So in particular, the pump, so the A0 and A0, it can do exactly what it was doing before. It just creates a pair of particles, they spread out and then recombine. I have to be, however, a bit more careful about the probe, about between tau and t plus tau, because if I just treat my wave packets as spreading ballistically, I would get that 0. It's impossible to recombine them because they just drift away. So one needs to be a bit more careful and go into a path integral picture where I just treat the fluctuations of these trajectories. Okay, but this is essentially a technical detail at this point. So how do I make this process connected? So again, as I've drawn this is disconnected. There is no interaction between the red and the blue, but I can make it connected using braiding. So in particular, if the blue trajectory pierces this kind of blue-red loop, I will get a factor that is a -1. And this is entirely due to the braiding phase. And note that I am not requiring the blue anion and the red anion to come close to each other. So this is just a purely topological effect. And then my claim is that these processes contribute to t to the 3 alpha enhancement. And this is because, again, of the integration over the initial position R. So this integral is, again, piecewise constant in R. And so the integral will be proportional to the area here in green, for which I have the loop threading. And okay, so here if one does the path integral calculation carefully, one can see that this is proportional to t to the 3 alpha. And again, this t to the 3 alpha really requires some local interaction. If I just had contact interactions, I would have a perimeter contribution rather than an area, and that would be at most proportional to t. Okay, so the reason why we are quite excited about this second result is that maybe it could be a way in the future to measure ionic statistics. And if you have ideas, objections, and comments in general, I would be very happy to discuss. This measuring Gaussian statistics in general is hard. It can be done in some fractional quantum Hall states using a state interferometry. But in more general setting, like in quantum speed liquids, I don't think there are proposal at the moment for how to do it. And so maybe this measuring this kind of t to the 3 alpha exponent could be used as a unique signature of anyons. So let me just conclude by thanking all my collaborators, in particular Sid and Sarang that organized this workshop. And let me also thank especially Max McGinley that really did the bulk of the work in this second project on the onions, and Fabian Essler in Oxford and Roman Vasser at UMass. So I will just leave you with a summary and thanks.
So for the second result, what are the necessary conditions on the dynamics of anyons for this to not break? It seems like, let me be extreme. Suppose the anyons are localized.
Right. Okay. Then it doesn't work.
Okay.
Okay. So what I'm using is that the anyons. So what I'm using. Okay. So there is an important assumption that I did not discuss, which is I always assume that the system is clean, so that. And in general, there is no obstruction to ballistic propagation. So I'm always assuming that if there are no particular constraints, then quasi-particle move ballistically.
If the anyons were diffusive, you would still have just a different power, but there would still be something.
Yeah, that was my next question.
Yeah, so I
more realistic, I feel.
Yeah, so I think that if the anyons were diffusive, then this would probably. So okay, but again, this is a speculation. This would probably be proportional to t, and the interaction term would be proportional to square root t. But again, speculation.
So, from as an experimentalist, in an experiment like of the type we've heard about from Kota or Andrea, or other people doing 2D spectroscopy, what would be the signature of this t to the 3 halves?
Right. Okay. I mean, maybe the simplest thing is if you did not do the Fourier transform, but just looked at the real-time signal. I think maybe that's the clearest signature, in a sense. Or another possibility would be to. So because in frequency space, this just manifests itself. So these divergences in time just manifest themselves as kind of power law thresholds at the, let's say, at the mass frequency. But then probably measuring the difference between omega to the -3 from an omega to the -2 is not super easy to do.
What are the power laws in the Fourier transform?
So let's see. So if you, so the simplest case where you, so if you don't have any divergence, let's say that you have an omega to the -1. So when you have a t, it's an omega to the -2, and when you have a t to the 3 half, it's an omega to the -2 plus 1 half. So it's 5 halves. Yeah, 5 halves. Thanks.
So you had a graph a little bit later where you show a growing oscillation. Is that
right? Yes.
So what experimental observable are you? Is that an experimental observable? That
yeah, I think. Yeah, I think in principle one. Okay, I mean in this super idealized case, yeah, this is something that one would be able to measure in an experiment.
It's the nonlinear response coefficient as a function of time delay.
Actually, could I ask another question? So when I look at this plot, the way this looks to me is that you're taking the system at some earlier time, and then you're watching it kind of like, I don't want to say thermalize because this is 1D, right? But it equilibrates to some kind of an ensemble that is, pre-thermalized, right?
Yeah.
And so the growth of this correlate is somehow like some measure of virtual like excitation in the bath, in the background. So with right, so you didn't show this plot for the anyons, but I thought the whole point of having anyons was that I can kick the system locally and I'm not gonna destroy topological order. So if this correlation function grows,
You dump energy density in the system, you can kill topological order, right? Finite temperature doesn't exist.
oh, because it's 2D, you're
Yeah,
saying.
it's very
Yeah, I see.
You can-
Right.
Energy density will kill.
And it's a global quantity, so yeah,
Yeah, exactly.
Oh, so yeah, you should do local quenches. No. Safe.
Other questions or comments?
If you do this for quantum Hall effect, for example, for Lofgren quasi-particle,
Right.
then what would you expect?
So okay, the short answer is I have no idea. So the reason is again this this assumption of ballistic propagation. So my understanding is their quasi-particle and quasi-holes are immobile. So yeah, I'm not sure what would happen there, but I think this picture kind of would not apply there. Definitely.
Either immobile or they do cyclotron orbits.
Yeah.
Screwed, right?
Yeah.
Also, you need them to be gapped, right, so that they can't decay to anything.
Yeah.
Other-
Yes. Yeah.
So do we expect though, I mean, in a real, I mean, could I think about doing this experiment in cobalt niobate, a 1D chain in a real material, or we have lattice and,
No. Yeah. Lattice effects should be fine.
yeah, I'm sorry.
Yeah,
I-
1D.
Yeah.
This experiment,
Yeah.
the 1D one, right?
Yeah. Lattice effects are not a problem. Yeah.
Phonons and all of these things that will thermalize the system.
So of course, okay. So let's say that you're. So of course, there is a. So you're introducing another kind of time scale.
Yeah.
And so I think this effect will be. You should observe this effect until the time scale that.
What's the time scale? I don't have a good feeling of that inverse of it, like.
So let's say
this
that.
path of acoustic phonons there, so it's inverse to the Debye frequency. or
So
something?
your
That's
true point function without the pump.
Yeah.
That will have a decay time scale, right? That's the time scale that I'm talking about.
Yeah, but what is it set by? What are these time scale that it's set by?
So for example, if you're at fine temperature, that is set by the density of thermal quasi-particles. So that goes, that is exponentially suppressed, like e to the minus gap over t, I think. With phonons, I haven't thought about it, but I would guess probably you can just do Fermi-Colton rule. So it's probably the phonon particle Kaplan squared.
Okay. I forgot how you do. Did you define it in a way that in equilibrium this is zero?
No.
No,
No. Okay. I don't know.
In other words, if you had a system that was generic, that was actually thermalizing. Yeah, sorry, I'm just processing the fact that you said, you would expect that it goes up and then kind of like just decays. Like if you couldn't define it so that it's.
No. Okay. So the point is C kappa is something that eventually goes to zero in the C to infinity limit.
Right.
But C0 doesn't. So that's essentially the why